while Lewis structures give us a great indication of where the electrons are going and how bonds are forming, they don't do an adequate job of telling us what a molecular shape is. And the shape or the geometry is going to have very, very important practical applications when we look at how molecules react. So we need to expand that Lewis theory a little bit farther. And the theory we use is called valence shell electron pair repulsion theory. And this is why when we look at our particular molecules and when we're drawing these structures, we need to really focus on the electron pairs. And this is what VSEPR theory is going to tell us, is that electron pairs repel each other and assume an orientation about an atom to minimize repulsion. The particular geometry a molecule adopts is due to this repulsion. And when we look at repulsion, we have to look at the lone pairs on a central atom and the bonding pairs on a central atom. And we find that the greatest amount of repulsion is between two lone pairs. So a lone pair repulsion is greater than a lone pair bonding pair repulsion, which is going to be greater than a bonding pair repulsion. So when we look at VSEPR shapes and molecular geometries, the electron pairs are going to dictate how the molecule's formed, and it's also going to dictate how the ligands orientate themselves in 3 dimensions. So the shapes that we can look at can be summarized in a chart. So we need to look at the total number of electron pairs, which sometimes are referred to as electron domains. So this is the total number of electron pairs around a central atom. The molecules that we'll look at in this class either have 2, 3, 4, 5, or 6 electron pairs around the central atom. The geometry that's going to be adopted from these pairs, or we should say here the electron domain geometry, if we have 2 pairs, a molecule is going to be linear. If we have 3 pairs, we have a trigonal pyramid. If we have 4 pairs, we have a tetrahedron. If we have 5 pairs, we have a trigonal bipyramid. And if we have 6 pairs, we have an octahedron. In addition to the electron pair geometry, we can determine the hybridization. If we have a molecule with a linear electron domain geometry, we have sp hybridization. If we have a trigonal pyramid geometry, we have an sp2 hybridized molecule. If we have a tetrahedron, it's an sp3 hybridized molecule. if we have a trigonal bipyramid molecule, there's an sp3d hybridization, and for an octahedron, we have sp3d2 hybridization. So in this VSEPR theory, we're going to be very, very concerned with this electron domain geometry, but we're also going to be concerned with something called a molecular geometry. So let's go back to our ammonia case, and in that ammonia case, we drew the ammonia molecule that looked something like this. So in this case, we have the ammonia central atom, and there's 4 pairs of electrons around the central atom. So if we have 4 pairs around the central atom, our electron domain geometry is going to be a tetrahedron. And if we have a tetrahedron, the hybridization is going to be sp3. So we now need to know what our molecular shape is going to be. And if we look at a 3-dimensional drawing of a tetrahedron, we have a molecule that's going to look something like this, with 4 ligands, where one is going to come out of the page and one is going to go back into the page. So each of these bond angles right here are 109.5 degrees. So we are going to have a nitrogen molecule in the center, and it's going to form 3 bonds to hydrogen atoms. So it's going to look something like this. The electron domain geometry tells us that this electron pair that we represent with a straight line up here in our Lewis structure is actually going to take up quite a bit of space. And it's going to take up just as much space as these hydrogen bonds do. So we're going to have an electron domain geometry of a tetrahedron, and our molecular geometry is going to be trigonal pyramid. And trigonal pyramid is this tripod-looking shape that has the base of a pyramid. And it has a triangular base. So these are the things that VSEPR theory is going to help us with, and we're going to go through a slew of examples of these molecular shapes, and we can go through and we can determine several things. We can determine the molecular geometry, the electron domain geometry, the hybridization, all of the bond angles, and whether or not a molecule is polar or nonpolar. And in the next several videos, we'll go through many examples of these different shapes of molecules.